Go. Hello, everybody. So then in this particular sequence of videos, we're going to talk about linear transformations. So this first part, though, I'll give a justification for why we want it. And then in later videos, I'll go show you what the actual definition is, how to compute them, and how it connects with what we've already discussed so far in this class. So currently, the way matrix multiplication has been presented to you is numerically just crank out the multiplication. It's also been defined as a way to sneakily write linear combinations of columns of the matrix. It's also seen as an algebraic process to go about solving linear systems. Thing is, though, is that there's a good geometric reason why you want to learn matrix multiplication. You can think of it kind of like a mapping. It's a transformation. It transforms a vector x into a new vector a times x. What we want to do is we want to focus in on the type of transformations, these mappings, that are compatible with what we have already discussed. Mainly, we want it to be compatible with vector addition and ultimately linear combinations, since that's sort of a tie-through thread through all our different topics. So just as an example, so you understand what I mean, if I give you the matrix A, as you see here, and the vector U and V, then it's pretty easy to see that A times U is V. So you can think of it as not just as multiplication, but as an action. When you multiply a vector on the left by A, it takes that vector and maps it to a new vector. So U in R2 is sent to V in R3. Now, we can discuss this more generally. I just give you a generic vector in R2. So that'd be x1, x2 as the components. And then the matrix multiplication of A times that vector will give you a vector in R3. So this matrix multiplication then shows how that the vector x1, x2 in R2 is transformed into a new vector in R3 that just has x1, x2 in it in order to determine the components of this vector in R3. Now, this means that matrix multiplication can be thought of as a way to make a new function. It assigns a vector in this space to a vector in that space. So we can describe that action then as function notation. So the common way to do that is to define a transformation. You may not remember this in algebra. The way you define functions is you use a lowercase letter or uppercase letter, and then you define what space is coming from, what's the input space and what's the output space. You don't see that very often in algebra, mainly because you really only ever work with real functions. You send a real number to a real number. So there's not really much point in that course to ever describe specifically where you're coming from and what type of things you're going to. But using that notation, we need to here because we might have multiple different spaces we're coming from and going into. So the function t sub a is a transformation that sends vectors in R2 and sends it into vectors in R3. And the mapping is done as you see here. And there's two ways to write it. The one on the left is by writing everything out in components. The one on the right is much more compact. The thing is, though, the one on the left, it's hard to read because the left-hand side has parentheses and then brackets and then the entries. It's hard to read that. So oftentimes on the left-hand side, we will ignore the outer parentheses. So it's like the transformation is applied to the vector and turns it into a new vector. But on the right-hand side, we will still always use parentheses around those vectors. We're always going to do at least that much. So that if you have components, we will drop the parentheses. If you don't have components, we always use parentheses because it's still a function. It's still a function of something and it gives you a result. Now, we want this transformation to be compatible with linear combinations. That's again, the kind of a running thread through all the different concepts. So recall that if you give me two vectors, u and v in R2 and any scalar, then these two properties are true. This is just basic matrix multiplication. So of course the matrix distributes through the sum, and of course the matrix distributes through, kind of pushes through the scalar multiplication. Scalar multiplication just comes out. But the transformation I just gave you was this action. So you can write the exact same thing with the function notation I just gave you. So the transformation I just gave you automatically satisfies these two properties, that the function distributes through sums and it kind of pulls out the scalar multiplications. Because of those two properties, this means then that this particular transformation between these two spaces in some way preserves linear combinations, because whatever the scalars were in a linear combination in a sum of vectors in R2, you would then get a new linear combination in R3, but the scalars are exactly the same. Again, remember that this part here, that's in R2. So it's a linear combination R2. But this vector and this vector and so on, all of these are in R3. So the whole thing here, that's a linear combination in R3. But notice that the scalars used, the coefficients used in this particular linear combination are exactly the same. Oh, that should be CK, and that should be CK there too. UK there too. All right, and I believe then that gives you a basic introduction for what linear transformations, what transformations are going to be for us. They're going to be a kind of a mapping, and in the end is going to preserve linear combinations. So I believe that's enough for that video.